Okay, welcome back everybody. So we're going to pick up with ancillary statistics. Just as a reminder, you've got a homework assignment out right now, the simulation study delta method versus Bayes versus Booth. If you haven't started by now, if you don't start by today, you will not finish on time. And so it's not a project that's meant to take 20 hours all at once. It's a project that's meant to, you spend 2 hours on it. You spend 2 hours on it, you spend 2 hours on it. And you do that for several days in a row, and then you can write up the report. There's a lot of information to digest. So the reason I say that you won't finish if you don't start real soon is because things go wrong in every single one of the examples. And so, and the question is when do these methods fail? So that's what this whole class is about. Comparing different methods and seeing their when they work, how you can bias methods and maybe accomplish something, how if you don't do that, maybe a method will fail, so on and so forth. So as an example, if you're doing a bootstrap or something like that, n is small, p is small, you're probably going to get all zeros. Let me do it the other way around. Let's say p is big, n is small, you're probably going to get a whole bunch of ones, and so the denominator in that thing you're estimating is going to blow apart. So half of your job is to report when the method works, when it fails, and then make a determination about what you prefer, what would you do. And so I leave it a little bit open-ended for you to answer those questions. Some of the answers that I might report if I were doing that assignment would be like I would just steer away from the mean. If the mean didn't exist, then you report something different. So, good example is the Bayesian method. So if you're doing Bayes and you're basing your inference off that beta prime distribution, there are some situations where the mean won't exist. But the posterior exists no matter what. And so if the mean didn't exist and I wanted to report some summary statistics, instead of reporting the mean, I might report a median. Or I might report just credible intervals and see how often they cover. So I might say I'm going to move to intervals, a range of answers, and see how often they cover. So that's kind of a weird thing to do, is see how often your Bayesian method, or see how reliably your Bayesian method creates intervals that cover the true answers. So that's kind of a frequentist way of looking at things. And so again, one thing I want to untie you from is that Bayesians can't be frequentists, because they can't. They can be optimal frequentists. So one thing you could do in the Bayesian analysis is change the hyperparameters of the prior. And so if I crank them up to be something like a beta 2,2 in the conjugate prior, the mean would always exist, but you would have to bias your answer pretty severely to do that. If n was small, that might not be the right thing to do. So there's many ways to report your answers. There's many correct answers, but this is a comparative thing, which requires you to think about it. So get started on that. I'm going to post some other homework problems, and we'll do a review session next week. So review session next week might be a good time to talk about what you might report in this simulation study. What do you do with all these, collections of data that you've simulated? So what happens when something doesn't work? What would you report? In my world, that's all I do for a living. So I write papers discussing the relative merits of different methods. So if I build a new method, I have to compare it against something, and I have to talk about the relative pitfalls. So what I don't like is papers that say this method is perfect and everything else fails, because they're probably just showing you one collection of examples. So in this case, I think it's a little bit better. Everything fails in slightly different ways. What's kind of nice about it is n is moderately large and p's near the middle. So those clean problems that you might see in a Stat 101 class, all the methods tell you the same thing, more or less. They're a whisker apart from each other. And so as n goes up, all the methods converge into each other. So there's this asymptotic relationship that everybody shares. So hopefully that's good food for thought. Okay, any questions before we start out on ancillary? Okay, let's go back to this
When do we receive our midterms?
Next week.
Awesome.
So, yeah, I'm about halfway through with them. I just want to go through them again. and make sure that there's no visitors visiting us when I return it to you. So I don't want to get mobbed right afterwards. So just happen to have done this before. So I'm also a frequentist. I know it's going to happen. So,
are we going to have a review session on Tuesday?
Yeah, why not? So I think it would be a good time to catch up on the simulation homework and anything else that's dangling. And then we'll probably do another review the week after to go over book problems. So hopefully that'll be useful to everyone. Okay. Let's just start with our example that we were looking at last time. This example is in the book. This is an example we keep coming back to, and I really like these examples because these inferences are a little bit difficult too because theta defines the boundary of the space. So just as a heads up, asymptotic frequentist methods usually suffer in these contexts. You usually need to penalize them. We'll be talking about that when we get to chapter 7. We're almost there. So xi, uniform theta plus 1. So just to clarify what I said, if we were estimating mu in a normal distribution, mu doesn't define the boundary, it's the center of the distribution. And so everybody that does inference on mu in a normal distribution basically agrees x bar is a good answer, unless you happen to know something and you want to inject some extra information. So this problem is entirely different because theta defines the boundary of the space. So these xi's live between theta and theta plus 1. So this is just a uniform distribution living between these two values. The interval length is 1, so the height of the density is 1. So this is going to be f of x given theta, and I'm going to collect n data points from this. We will say everything is IID in this example as well. So I'd see data that looks something like that, and if I drew a histogram, it would maybe look relatively flat. This is actually a good exercise, I think, for our statisticians to do, is to just stare at histograms sometimes for uniform distributions and see what uniformity looks like. If you actually did do this and plot it, it wouldn't look perfectly flat. It would look rather jagged. The question is that uniform? And so getting a trained eye for what data actually looks like is a skill you should develop. So I think simulating all this stuff all the time is probably a good idea. If you do this in high dimensions, 2 or 3 dimensions, you'll notice uniformity clusters. So there's pockets. So it's kind of a weird phenomenon. Okay, or it appears to cluster. So we can talk about that later on. Okay, so here's the problem set up. We worked through last time what the joint distribution is. The joint distribution for everything where cap x is just x1 through xn, this collection of data points. This is just going to be the product. I goes from 1 to n, 1 over 1 in this case. It's the interval length, so it's just that. And we already know that we're making a mistake if we just leave this thing right here. So the density is 1. That's just the fxi's given theta. And the big indicator to you that this is a mistake is there's no thetas over there. So this can't be the joint distribution because the joint distribution has a relationship between theta and x's. And a likelihood function inverts that relationship. And it talks about the function of theta given the x's. And so there's no thetas in here. So if I were staring at this, I would say you've got a problem. So where do we fix it up? It's by including this part of everything. So we need to write that into our function and constrain everything. So the xi's live between theta and theta plus 1. And so all of them do that. So I'm just going to re-encode this real quickly, that this thing right here is just this product of this indicator function, where this is a 1. If xi's live in this range right here, So this expresses a relationship in terms of x with respect to theta and vice versa, the relationship between theta with respect to x. And this is a 0 otherwise. Just an indicator function. So this is just this same exact thing. And so this means that all of the data points live between theta and theta plus 1. And I think you know what I'm going to do with this. That this same thing says something about the minimum. So let's say, I've been through that one. Let's put it right there. There's my minimum. And there's my maximum. We've given this some notation. We've called that xn. I'll use the same n that I used before, cap n. And this right here is just x1, the minimum. Hey, quick question. Are you familiar with order statistics?
Yes.
Okay, good. So, awesome. So this won't be so elusive. What we've learned way back when is what the distributions of these order statistics are, and we know the distributions of the joint order statistics. And we can write all that down. And so I'm going to cut through that part of the lecture because everybody has seen this a couple times in this class. So this whole thing is the same thing as writing down an indicator function that x, our minimum, is greater or equal to theta, and our maximum, xn, is less than or equal to theta plus 1. So max is less than the boundary, and the min is greater than the boundary on the left-hand side. And so what we see from that, if I'm thinking about this as a relationship in terms of theta, if I think about it in terms of a function of theta, the whole likelihood function is just this indicator function. That's everything. And so you can think about that a little bit. So this likelihood function will place like a flat ridge in there of saying where are valid values of this theta. And the more and more data I collect, it's going to tighten the bounds on that ridge. And so if you have trouble visualizing that, you should simulate it and plot it. So that's what I usually tell people to do with these sorts of problems, is simulate it, plot it, and think about the likelihood function. That's a theme we'll come back to over and over again. Okay. So we can see from this that the only dependence of theta on the x's comes from the min and the max. So the min of x is equal to x1, and the maximum of x, all of our data is xn. These are minimal sufficient. Now I've done something in my head to convince myself of this. What I've done is I've applied the factorization theorem in my head to look at this. That this term is going to factorize out, and that's going to be the only dependence on the data for the likelihood function is the min and the max. So I've applied the factorization theorem. What's the constant that just depends on x? So that's h, that's 1. And so, and this is going to be that g function that connects the sufficient statistic to the parameters. Then I did another thing in my head. I convinced myself real quickly that that dependence is always going to be there between the min and the max and theta. And I'm never going to be able to reduce that any further. If you were to convince yourself that this is minimal sufficient, then I'll allow you to do what I just did, this mental calculation, and I'm already convinced that this is minimal sufficient. I'll allow you to do that for the rest of your career so long as on a midterm, your next midterm or your next final or your next qualifying exam. But once you've done it there, you are free to just do this as a mental exercise. So, but on a midterm or a final, what I want you to do is use the condition that I stated last time on minimal sufficiency. So you're going to have to check that ratio condition, show that it's a constant with respect to theta, if and only if the mins and the max are the same in the two auxiliary data sets. There's a definition in the book that we can say. So that's what you would do on an exam, and you would verify that. I would say it's a good mental exercise, even though I'm not assigning it for homework, they do this in the book, is convince yourself that that's true. So we know what the minimal sufficient statistic is. Leave this up. Okay, another minimal sufficient statistic. So as we learned, minimal sufficient statistics are transforms of any other sufficient statistic. And so one-to-one transforms of minimal sufficient statistics are minimal sufficient. That should be fairly obvious. We don't lose any information. So here's another minimal sufficient statistic. And this is about what we studied from the very beginning of class. So the range, which is xn minus x1, and the mid-range, which is the arithmetic average of the max and the min. Just to repeat myself one more time, this example is set up just to show you certain features of statistics. I would never use this statistic for anything. So this is just a cookie cutter example to demonstrate some points. I might use the range, but this is really weird because I have order statistics and then I'm averaging them to give me a measure of the middle, but I've got a better measure of the middle if I used order statistics, and that's the median. Okay. We learned a long time ago what the distribution of these things are for a slightly different problem, where I was looking at a uniform distribution between 0 and theta. It was very similar. So let me just write down what that joint distribution is. You can go back to chapter 5 and convince yourself this is the right transform distribution. We spent a lecture on this once upon a time. So the joint disk of R and M. So again, what you're going to do is you're going to do the inverse on these, solve for x1 and xn, plug them into that joint distribution, that density formula for the joint distribution on x1 and xn, the min and the max. I'll find the Jacobian once I do this inverse transformation. The Jacobian in that case was 1. We did that once upon a time and showed that that Jacobian was 1. Plugged everything in, and from those steps, you get this. So several steps that you need to do to convince yourself of this. So this is going to be n times n minus 1, r to the n minus 2, and there's some boundary conditions in all of this. R is going to go between 0 and 1. This is slightly different than the example that they presented to you in the book, where this would be going from 0 to theta. And then you could rescale it if you wanted to. And they do that eventually in the book. So in the mid-range, those between some other bounds, this is going to be theta plus r over 2. And this is going to be theta plus 1 minus r over 2. I cannot see that off the top of my head without doing a calculation and drawing a picture. Same picture that we drew a long time ago, same calculations that we did a long time ago to figure out what these boundary conditions are. So these are defining that triangular wedge that we simulated and worked out in class. So these are the bounds. And so from this, you can see that there is a dependence on theta. You don't see it up here, but you see it in the boundary condition. So theta again is defining the boundary in this transformation. And so you would need to write that down. If I were just staring at this, I would know, and somebody said that the bounds didn't depend on theta, I wouldn't believe them. Because this doesn't depend on theta. The mid-range and the range are minimal sufficient, so they should have information about theta. And they should have all the information about theta. So this problem, this transform problem, still encodes all the information about theta, and theta lives on the bounds. Okay, so I think if we can digest this and remember where this distribution came from, everything else is relatively straightforward in this example. So let's look at the marginal distribution on the range. It's just this. And I'll write this down, implying that there's some dependence on theta. We'll notice at the end of this, there won't be that dependence on theta. So this is n times n minus 1, range to the n minus 2. And I'm going to integrate over the mid-range. And that's going to go from theta minus r over 2 to theta plus 1. This is the other way. Plus, and this is minus r over 2. So that's a pretty easy integral to do. So I'll just do this, r to the n minus 2. I integrate over m, there's no m's there, so easiest integral in the world to do. And then I'll just solve the bounds of this. So this is going to be theta plus r over 2, and theta plus 1 minus r over 2. So I'll just take this ultimately and subtract that from that. The thetas will cancel. There'll still be a 1 sitting right here, and the r's will add up. The negative r's, in fact, will add up. And so this is going to look like this. N times n minus 1, r to the n minus 2, 1 minus r. So ultimately, this whole thing right here is just 1 minus r. And the dependence on r is still, it lives between 0 and 1. So here's our distribution. N times n minus 1, r to the n minus 2, times 1 minus r, and r lives between 0 and 1. And so what we see right away is the range has no information about theta. So, and we probably could have convinced ourselves that that was true. And there's a lot of ways to do these problems. So technically speaking, if you wanted to fully demonstrate that a statistic was ancillary, the definition of ancillarity is a statistic is ancillary if its distribution, and I want to say this really clearly, its marginal distribution doesn't depend on the parameter space. If that's the case, then the statistic is ancillary. So it appears that that statistic has no information about the parameter. That's almost a true statement. That's what I want to untangle. So what we see from this is R is ancillary. It falls into that definition. There's no dependence on theta. And if we think about the original distribution, theta and theta plus 1, and we see all these data points in here, the range right here is telling you something about the spread of this distribution. But if I take theta and I move it linearly, it just shifts this whole distribution linearly. And so theta itself is a location parameter. In the old example where x's lived between 0 and theta, theta was a scale parameter. In this context, we've changed it to a location parameter. And the range is really saying something about scale of the distribution. So if you did this the other way around, obviously the mid-range has information about theta. And I think we can convince ourselves real quickly the mid-range is not ancillary, but the range itself is ancillary. So this is ancillary. Now the reason we're covering all of this is because in just thinking about statistics and the properties of statistics, this is interesting. So if you were Fisher back in the 1930s, he's going to ask himself all these questions. Which statistics have all the information about theta? Those are sufficient statistics. Can I compress it and have a lower dimensional representation of the sufficient statistic? And how far can you reduce it? That's the minimal sufficient statistic. That's the min and the max, or the range and the mid-range in this case. And so in that same vein, if you were Fisher, you might ask yourself, which statistics have no information about theta? And those are called ancillary statistics. Here's the part that he struggled to understand for a little while. That those two statistics, maybe you think they live in non-overlapping spaces, but they do not necessarily do that. And I'll show you the condition by the end of this lecture that demonstrates when they do live in orthogonal spaces. So let me just ask you a question. I've kind of given you the answer to this, but I'll try to demonstrate it better in the next example. So question, does the range, I'll just say R, have information about theta? What do you think? It depends. Yeah. So this is the tricky part of understanding ancillarity. In the presence of the mid-range, it does. But on its own, it doesn't. So on its own, it has no information. There are statistics out there that no matter what you do with them, they can never supply information about theta. This is not that example. So the range does supply information about theta so long as the mid-range is present. But on its own, it doesn't supply any information. And this is the thing Fisher was grappling with, and trying to understand that and mathematically characterize it. So he does something brilliant, and he figures out something fairly brilliant. What do you do with it? Nothing. It doesn't make you a better statistician to understand all of this stuff. So I should say there's something called the conditional frequentist out there, and it conditions on an ancillary statistic, but you need to choose the right one, and there's no formal paradigm for exploiting that. And so I will say this, if you're a likelihoodist or some form of a likelihoodist like a Bayesian, when you condition on all of X, you've conditioned on all the minimal sufficient statistics, the sufficient statistics, the ancillary statistics, you've conditioned on everything. Next time we'll go into something called the conditionality principle, and it'll exploit that. So the answer to this is marginally it doesn't. No. But in the presence of M, it does. So you can chew on that for a while. So on its own, it doesn't. And that's what I mean by marginally. Let's look at another example and see if we can understand this a little bit better. Similar example. Let's say the probability of x can be equal to theta, or x could be equal to theta plus 1, or x could be theta plus 2. And I'll say all of these is 1/3, has probability 1/3. So this is a uniform distribution. And my interval length is a little bit different. I'm going from theta to theta plus 2. So, but this is a discrete problem. So I would say this problem is eerily similar to the other one. It's just a discrete fabrication of the other problem. So, and we can analyze this maybe a little bit easier. So just to be real clear, maybe this is a 4, this is a 5, or a 6. And each one of those outcomes is going to happen with probability 1/3. So it's just a coin flip. Okay, let's just think about a couple different scenarios. So let's examine what R can be. So R can take on 3 different values in here. So the range could either be 0, depending on if I see the same number. I should tell you what the sample looks like. So I'll say we're going to collect. I'll make it really simple. We'll collect x1 and x2. And we'll call this cap x. So I only get to see 2 samples. So let me rephrase everything. There's 3 possibilities here. So either I see the same sample twice, that's pretty likely to happen, or I see this one and I see that one, or I see this one and I see that one, or I see this one or I see that one. And so the range can either be R can be, I'll say, R can be 1, R can be, let's start at 0. R can be 1, R can be 2. So and let's check out all these different possibilities right here. If the range is 0, then one of 3 things happened. So I'm going to look at the mid-range right here. There's 3 possibilities for the mid-range. So either m is equal to theta plus 2 divided by 2. So I either solve this one twice, or I solve this thing twice. Theta plus 1 plus theta plus 1 divided by 2. Or I can see this. Theta plus theta divided by 2. Easiest averages in the world to take. This is theta plus 2. This is theta plus 1. And this is theta. So if the range is 0, the mid-range could take on any one of those 3 values. What's the probability of this happening? Let me think about it for a second. So you could go through a formal calculation and do this and table everything out and figure out what the conditional distribution. So this is the conditional distribution of the mid-range being theta plus 2, given R is equal to 0. So you could work through all of that and do that calculation. So you could figure out the joint distribution, table everything out, all the different possibilities, And then you can marginalize and figure out the conditional distributions and work through these probabilities. And if you were in a Stat 101 class, that's how they would teach you about conditional distributions. So let's not do that. Let's see if we can just think about it. Think about the symmetry right here. What's that?
It's just 1/3.
It's just 1/3 for each one of them. So let's just think about it. So I'm going to get one of these values no matter what. What's the probability that I'm going to match that value? It's 1/3. So each one of these is 1/3. So this is the probability. 1/3, 1/3, 1/3. Let's do this. Range is equal to 1. Same sort of thing. So I could have the mid-range could be theta plus 1 plus theta divided by 2. So if the range is 1, this example is that I got a 5 and a 4. And so this is going to be equal to theta plus 1/2. The mid-range could also be, the range could also be 1 if I saw these two numbers right here, a 6 and a 5. So the mid-range would be, in that case, theta plus 2 plus theta plus 1 divided by 2, which is theta plus 3/2. Let's do the same mental exercise. Again, if you wanted to formally do this and you're in Stat 101 class and learning about conditional distributions for the first time, this probability would be the probability of given R is 1, what's the probability of M being this value or that value. There's a certain symmetry to the problem that makes it a lot easier. What's this probability? 1/2. Okay, last one. The range is 2. This is the most compelling one. So if the range is 2, if somebody came in and told me that, then I could compute the mid-range. Right here, I would know the problem setup, presumably. So again, I'm supposed to know what the model is. That's the fiction in this class that we keep repeating. So later on, you'll have to build that model. So there's only one possibility. I would see the 6 and the 4. And so this would be, the mid-range would be theta plus 2 divided by 2, which is equal to theta plus 1. And this happens with probability 1. So if I just invert all of this stuff right here, I can come up with an estimate of what I thought theta was. So for this right here, I could say for the range is equal to 0, I could say if I could estimate theta by taking the mid-range, I could subtract off 2, or I could subtract off 1, or I could subtract off nothing. So this is all this example right here. And so this happens with probability 1/3, 1/3, 1/3. For this, right here, I can try to solve for theta just by inverting all of this, i.e. subtracting. And so I can look at the mid-range minus 1/2, mid-range minus 3/2. Each one of those things happens with probability 1/2 and 1/2. And then our most compelling example is this one. So the mid-range minus 1, again, just inverting right here, solving for n. So that's the mid-range minus 1, and this happens with probability 1 right here. And so by looking at this, you can see instantaneously the range does have information. But in the presence of the mid-range, it does. So if you told me the mid-range, and you told me the range right here, I would say if we looked at the range being 2, I would tell you deterministically what thing it was, so long as this was the right problem set up. And so the range does supply information, but in the presence of something else. And we've said that the same way, or different ways, a couple times now. So, what this shows you is that so I should say, so the ancillary statistic does provide information in this example, provided the mid-range. So conditioning on the range could give you information. On its own, if I just give you the range, you can't say anything about theta. So, because it's ancillary. Let me tell you what Bassu's theorem is. We are not going to go through the proof of Bassu's theorem. Next time when we come in, I'll give you an intuitive understanding of what this condition says. Right now, it's going to look rather elusive to you. And I want you to go home and just kind of think about, what does this condition say? Maybe you might read that passage, but if you decide you don't have enough time and you can't read about Bassu's theorem, this is a good place to save time. I won't test you on it other than the statement of Bassu's theorem, so there'll be no proof. And the reason I do that in this class is not because it's uninteresting, it's just because it's unuseful. So it doesn't make you a better statistician to know this, but it does teach you something about probability theory. So I just want you to know what it is if somebody brings it up. If you ever encounter somebody where they say Bassu's theorem is the key to solving this problem right here, and it's a real engineering or medicine or science problem, tell me about it, I will be flabbergasted. So I've never seen any utility come out of this, but I still think it's interesting from a mathematical perspective. So let me tell you about complete statistics first. In my 20 or so years of being a statistician, nobody once has ever said, oh, you've got a minimal sufficient statistic, is it complete? You know, I would feel really good about that. Then there would be no ancillary statistics that overlap that thing. Doesn't happen. So again, it's not a real inferential tool. But complete statistics say this. So the expectation, so I should say a statistic Tx is complete if the expectation of GTx is equal to 0. And this is the part of this that is difficult. I'm going to give you a homework problem so you can just see the difficulty here in verifying something is complete. There's an example in the book. There is a solution in Casella and Berger, and I don't mind if you look at that one. So, because it can be rather difficult to prove completeness about something. The reason it's difficult to prove completeness is this is going to be true for any such G. So any such G that has this property right here, if I take the expectation of G of some statistic and it's 0, and this implies, so I haven't told you the rest of the definition, this implies that the probability of GTx is equal to 0 is equal to 1. Let me say this again. So a complete statistic is a statistic such that if I take a function g, I take the expectation of it, and it's 0, that's going to mean that g is actually 0 in probability. Now this is an elusive right here. That if I had the probability of something being 0. So the function itself is 0 in probability. If I go to take an expectation of that thing, of course it's going to be 0. What else would it be? But the other way around is a little bit harder to think about. That the expectation of this for arbitrary g is 0 will mean, and I would have to verify this, that the probability of that function being 0 is actually 1. And going through that and arguing that for all g is difficult. So it's a big functional analysis that you need to do. So again, I'll give you one problem on it just so that you're exposed to it and you can see the difficulty and why I don't test on this. This is actually the connection. And so it's a little bit weird, and I'm going to have to talk about this condition right here, what this actually means for something to be 0. So I want you to think about what this actually implies about the connection with data itself. We'll come back next time and I'll give you an intuitive understanding. Let me tell you what Basu's theorem says. So Basu's theorem says this: if a statistic is minimal sufficient, let's give this statistic a name, T of X, is minimal sufficient such that this is also true, that for any function g I find that the expectation is 0, that means in probability that function itself is 0. So if it's minimal sufficient and complete, the notation they use in the book is ancillary statistics are denoted by S. Minimal sufficient statistics or sufficient statistics are denoted by T. That these are going to be independent of each other. So what that means is if I look at the joint distribution of an ancillary statistic and a minimal sufficient statistic, they'll factorize. That's what we mean by independent of each other. So let's just read what this says. And then we'll move on to something a little bit more useful. If T is minimal sufficient and complete, then it's independent of every ancillary statistic. So I should say that. Every one. What that means is they live in different spaces. So this is probably what Fisher was thinking would happen no matter what. That ancillary statistics and minimal sufficient statistics live in different spaces. And he's wrong, if that's what he was thinking about. So then he concocted this and figured out this is the condition you need. So chew on that for an afternoon or so. Think about why that's true, but think about what this condition really says about everything and what its dependence on theta implies. So we'll come back and we'll look at this next time. And then I'm going to move on to the conditionality principle and the likelihood principle. I'm going to give you the likelihood principle light. If you ever show up in a conference where somebody starts talking about the likelihood principle, there's a fight about to break out. So be prepared for it. So a couple of years ago, we had Jim Berger come up from Durham. He gave a talk on the likelihood principle, and Deborah Mayo, who's a faculty member here, she's emeritus, she's retired. So was Jim, and they got into a fight as soon as he invoked the likelihood principle. And it goes on, and it goes on, and it goes on. And so I'll give you a paper to read if you're interested in about it, but I don't think it's very productive to just create paradigms where people just necessarily fight. So the likelihood principle is a little bit overstated. And so what I'm going to do is I'm going to rephrase the likelihood principle, and I'm going to give you what I consider the likelihood principle light, and there's really nothing to fight about if you just phrase it slightly different. So we'll discuss it next time. Depending on which day it is, either discussing the likelihood principle is my favorite thing to do or my least favorite thing to do. So we'll see what it is on Friday. Thanks, you guys.